the representation of oxidation number by putting a Roman numeral in parenthesis after the symbol of the metal in molecular formula is called Stock notation. Oxidation is the reaction in which the oxidation number increases and in reduction the oxidation number decreases. Which is undergoing oxidation, that will be the reducing agent, and which is undergoing reduction, that will be the oxidizing agent. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. Last session, we discussed about what is oxidation and what is reduction, right? And redox reaction in terms of electron transfer reactions. So we started off with discussing oxidation and reduction in terms of addition of oxygen, addition of hydrogen, or else removal of hydrogen or removal of oxygen, all that, right? And then we started discussing redox reaction in terms of electron transfer reaction. That means in oxidation process, what happens? There will be loss of electrons, and in reduction process, there will be addition of electrons or else gain of electrons, right? And reducing agent and oxidizing agent. What is reducing agent and what is oxidizing agent? Or else we can also call it as oxidant or reductant, right? Yes. And the oxidation number or oxidation state. How can you calculate the oxidation number? Right, using different rules that we have studied in detail in last session. So in today's session, we are going to study Stock notation, right? And then definitions of oxidizing agent and reducing agent in terms of oxidation number. Okay, in terms of oxidation number, we are going to identify which is the substance which is undergoing oxidation, reduction, or which is the oxidizing agent and reducing agent in terms of oxidation number, right? And then we are going to discuss the 4 different types of redox reactions as well in this session. So let's begin with the first one, that is Stock notation. So the oxidation state or oxidation number of a metal in a compound is sometimes presented according to notation given by German chemist Alfred Stock. So from that you get the name Stock notation. So what you're going to do is here you will be representing the oxidation number in terms of Roman letters. Okay, so the representation of oxidation number by putting a Roman numeral in parenthesis after the symbol of the metal in molecular formula is called Stock notation. Okay, so in the molecular formula, after writing the name of the metal, you are going to mention the oxidation number in Roman numericals. Okay, that means let's take an example of copper oxide, that is Cu2O. So the first step is we have to calculate the oxidation number, right? So once you get the oxidation number, we are going to represent it after writing the name of the metal in Roman numerals. So that is called as Stock notation. So let's see the oxidation number here. For oxygen it is -2, right? For copper we don't know, so we are going to keep it as X. So how many atoms are there? 2. So 2X minus 2 is equal to 0. It's not having any other charge, right? So 2X is equal to 2 and X is equal to +1, right? It's +1. So we got the oxidation number. So how we are going to write in terms of Stock notation? We write copper, right? So after writing the name of the metal, you mention the oxidation number in terms of Roman numerals, right? So this is how you mention 1. And after that, you write oxide. Okay, so this is copper 1 oxide. So this 1 stands for the oxidation number, right? Next one, FeCl2. For FeCl2, again, let's calculate the oxidation number. For chlorine, as it is a halogen, we already know it is -1, right? So for 1 chlorine atom, it is -1. Again, for iron, we don't know, so we are going to take it as X. X plus 2 into -1 is equal to 0. 2 into -1. Why 2 into -1? There are 2 atoms of chlorine, right? So X minus 2 is equal to 0. X will be equal to +2, right? So we got the oxidation number. So what it is written here? Iron to chloride. Okay, so this is how you represent the Stock notation. So now moving on to the next one, that is potassium dichromate K2Cr2O7. K2Cr2O7. Okay, so again, first step is we have to calculate the oxidation number. For oxygen, it is -2. For potassium, as it is a alkali metal, first group element, right? It is +1. So how many atoms of potassium are there? 2. So 2 into 1 plus, we don't know for chromium, so we take it as X. So how many atoms are there? 2. So 2X minus 7 into plus 7 into -2 will be equal to 0. Right. So 2 into 1 is 2 plus 2X 7 into minus 2 is minus 14, which is equal to 0. So 2x will be equal to 12x is equal to plus 6. Again, we got the oxidation number. So it is written potassium dichromate 6. Okay, so I hope it is clear. Moving on to the next one, manganese oxide. Okay, so as you can see, oxygen, it is minus 2, right? Manganese we don't know, so we take it as x. So how many atoms are there? 2. So 2x plus 7 into minus 2 will be equal to 0, right? So 2x is equal to 14, x is equal to plus 7. So manganese 7 oxide it is written. And the last one, tin oxide, SNO. For oxygen it is minus 2. So of course we know that for tin it must be plus 2, right? So tin 2 oxide. So this is how you represent the stock notation. So first of all, according to the rules, you need to be knowing how we can calculate the oxidation number. And just you have to mention the oxidation number in terms of Roman numerals after writing the name of the metal. So moving on to the significance of stock notation. So it helps to identify whether the species is present in oxidized form or reduced form. So this is the reduced form of this particular compound. So as you can see here, it is in the +1 oxidation state and here it is in +2 oxidation state. So using this, we can identify whether the particular compound is in oxidized form or reduced form. So now there are few examples given here based on which we have to write the stock notation for these compounds. So using the stock notation, represent the following compounds. So let's take the first one here. So as you can see here, HAuCl4. Okay. So Cl4, again it is halogen. So we know that it is -1. For hydrogen, it is +1. For gold, we don't know. So we are keeping it as X. So 1 plus X and 4 atoms are there. So 4 into -1 will be equal to 0. So X will be what? X is equal to +3. So how do you write the stock notation? HAu. After writing the metal, we have to represent the stock notation and Cl4. Okay, so I hope this is clear. So in Roman numericals, you have to write. Moving on to the next one, CuI, copper iodide. How do we write it? Copper, as we don't know, we represent it as X, and for iodine, it is -1. Again, it is a halogen, right? So X plus -1 is equal to 0. So X will be equal to +1. So it is copper 1I. Right? Clear? Now moving on to the next one. Again, oxygen, it is -2. Titanium, we keep it as X. So 2 into X, 2 atoms are there, right? So 2X plus -2 is equal to 0. 2X will be equal to 2. X will be again +1, right? So how do we mention this? Ti2,1, right? O. Clear? Right. Moving on to the next one, CuO, copper oxide. So it is -2 again, and here it is X. We don't know. So X -2 is equal to 0. X is equal to +2. So copper 2 oxide. Okay, so I hope it is clear. So this is how you represent the stock notation. Now moving on to the next one, definition of oxidizing agent and reducing agent in terms of oxidation number. So how can we define reductant or oxidant in terms of oxidation number we are discussing now. So in terms of oxidation number, when the oxidation number is increasing, we say that the compound is getting oxidized. Right, or the atom is getting oxidized. When the oxidation number is reducing, we say that it is getting reduced. Okay, so let's see, reducing a reagent which decreases the oxidation number of an element in another reaction is called as reducing agent. The oxidation number of reducing agent is increased during redox reaction. And moving on to oxidizing reagent which increases the oxidation number of an element in another reaction, and the oxidation number of oxidizing agent is decreased during redox reaction. So we have discussed about what is oxidizing agent and reducing agent, right? So what was reducing agent? Reducing agent is basically the compound which undergoes oxidation, right? So what is written here? Reducing agent is a reagent which decreases the oxidation number of another element. It decreases the oxidation number of another element, but it itself increases its oxidation number. So in reducing agent, what happens? It gets oxidized. That is, its oxidation number increases. Now moving on to oxidizing agent, it helps, or it is a reagent which increases the oxidation number of another element, but it itself undergoes a reduction in its oxidation number, right? Oxidizing agent will undergo reduction by the decrease in oxidation number. So let's take an example here. MnO4 minus plus Fe2 plus is giving Fe3 plus and Mn2 plus. So this is the reaction which is given here. So first let's find out the oxidation number of each of the elements present here. For oxygen we know that it is -2. For manganese we don't know, so we keep it as X. So X, how many atoms are there? 4, right? So X plus 4 into -2 is equal to -1 it is. It's not 4, it's a charged species, right? So -1. So X minus 8 is equal to -1. X is equal to +7. So we got the oxidation number as +7. Now it is Fe2 plus here already. Whatever this is the charge on the ion, that will be the oxidation number. We have studied this in the rules. So oxidation number here is +2. And Mn2 plus again it is +2. Fe3 plus it is +3. So oxidation number is clear. So now we are going to see which is undergoing oxidation, which is undergoing reduction. So here you can see it is Mn, manganese in +7 state, and here it is in +2 state. So what has happened from the reactant side to the product side? The oxidation number has decreased, right? From +7 to +2, the oxidation number has decreased. So that means manganese is undergoing reduction, right? Oxidation number decreased, so manganese is undergoing reduction. Now coming on to iron, what is happening here? Fe2 plus it is, that is oxidation number is +2. It is getting converted into +3, right? So what is happening? Oxidation number has increased, so it is undergoing oxidation. Iron is undergoing oxidation and manganese is undergoing reduction. So I hope it is clear. Oxidation is the reaction in which the oxidation number increases and in reduction the oxidation number decreases. So I hope it is clear. So now let's do a problem based on this. Justify that the reaction 2Cu2O plus Cu2S gives copper plus SO2 is a redox reaction. Identify the species getting oxidized or reduced, which acts as oxidant and which acts as reductant. Okay, so let's write down the reaction plus Cu2S gives 6Cu plus SO2. So we are going to write the oxidation number for each of this. So for oxygen it is -2, we already know that, and for copper it will be +1. How come? We can again calculate it. It is 2x, as we don't know, we are doing it as 2x. -2 is equal to 0. X will be equal to +1. Alright, okay. Now moving on here, for sulfur it is -2. So again, if we are taking is as x, so 2x minus 2 will be equal to 0, x will be equal to +1 again. So here also copper is in +1 state. Now here copper, it is in its elementary state, so it is 0, right? It is 0. And coming on to here, oxygen again it is -2, so x minus 4. By 4, it is 2 into -2 will be equal to 0, x equal to +4. So sulfur in +4 oxidation state. So till here it is clear, I hope. So now let's see what is happening to copper here. Copper is in +1 state in the reactant side and it has reduced to 0. From 1 it has become 0. That means what has happened? Reduction has taken place here, right? Reduction has taken place here. So what underwent reduction? Copper underwent reduction. Now moving on to sulfur, what has happened here? From -2, it has oxidation number has increased to +4, right? -2 to +4. So this is undergoing oxidation. Okay, so I hope it is clear. When the oxidation number is increasing, it is undergoing oxidation. It has increased from -2 to +4. So what does the question asks you to find? Which is getting oxidized? Sulfur is getting oxidized. Which is getting reduced? It is copper which is getting reduced. And which is the oxidant and reductant here? Okay, so which is undergoing oxidation, that will be the reducing agent, and which is undergoing reduction, that will be the oxidizing agent. So we know that copper is undergoing reduction. So this will be the oxidizing agent. So which is the oxidizing agent? It is copper oxide which is the oxidizing agent. Now what is happening to sulfur? It is undergoing oxidation. So copper sulfide is the reducing agent. So I hope it is clear. Now moving on. two different types of redox reaction. So the first one is combination reaction. So you already must be knowing what is generally a combination reaction, right? Yes, so two things will combine and form a new product. You might be familiar with what is combination reactions. So we are going to discuss in terms of redox reaction. So let's see, redox reaction in which chemical compounds are formed by the combination of two or more elements is called combination reaction. So two or more different elements will combine and form a new product. So in terms of redox reaction, we are going to see. So a simple example is taken here, combustion of carbon, that is carbon plus oxygen will give you carbon dioxide, right? So let's see C plus O2 giving CO2. So how we are going to discuss in terms of redox reaction, we'll see. In the same reaction, it is undergoing reduction as well as oxidation. In terms of oxidation number, we are going to see. So carbon again, it is in its elementary state. So it will be 0. The oxidation number will be 0. For oxygen, again it is in its elementary state. It is O2, right? It is not combined. So again the oxidation number will be 0. Now moving on to carbon dioxide, CO2. For oxygen, it is -2. Carbon, we take it as X. So X plus 2 into -2 will be equal to 0. X minus 4 will be equal to 0. X is equal to plus 4. So the oxidation number is plus 4, right? So let's see here what is happening. For oxygen, it is -2, right? So what is happening for carbon? It is getting increased. The oxidation number is increasing from 0 to 4. So it is undergoing oxidation. Carbon is undergoing oxidation. And for oxygen, from 0, it has reduced to -2. Oxidation number has decreased. So it is undergoing reduction. So I hope it is clear. Okay. Now the next example is combustion of methane. CH4 plus 2O2 is giving CO2 plus 2H2O. Okay. So let us write down this example here. CH4 plus 2O2 giving CO2 plus 2H2O. Okay. So CH4 for hydrogen it is -1, right? And carbon it will be +4. How come? 4 atoms are there. So if you calculate it, you will get -1 here. For hydrogen it is -1. 4 atoms are there. So to balance it, it will be +4. Oxygen again it is in its elementary state. So it will be 0. Carbon dioxide we already know. Just now we calculated. For oxygen it is -2. Carbon it is +4. For water it is -2 and +1. Right. So this is what we can obtain the oxidation number. So we can see here hydrogen it was -1. It has increased to +1. So what is happening here? Oxidation of hydrogen has taken place. And oxygen it was 0. It has decreased to -1. So here reduction has taken place. So this is how we can determine it. And the last example, 3Mg plus N2 giving Mg3N2. So here also magnesium, it's elementary state, so it is 0. Nitrogen also N2, so it is 0. And here if we calculate nitrogen, it is -3 and magnesium, it will be +2. Magnesium, we already know it is +2 because it is an alkaline earth metal. So how many atoms are there? 3. So 3 into 2 plus 2 atoms of nitrogen are there. So we take 2x will be equal to 0. 6 plus 2x will be equal to 0. 2x is equal to -6. X will be equal to -3. So that is what we have written here. So here also magnesium it has increased from 0 to +2. So what is happening here? Oxidation is taking place and nitrogen from 0 to -3 it has reduced. So here reduction has taken place. So I hope combination reactions is clear for you. Next moving on, the decomposition reactions. So these are redox reactions in which a chemical compound undergo decomposition. It can happen by itself or by an external source by heating it to give products containing at least one elemental state. So one reactant is getting decomposed to further smaller products. So let's see here, 2KClO3 is decomposed into 2 moles of KCl and 3O2. So here let's write it down. 2KClO3 decomposes to 2KCl and 3O2. So you can see here the symbol is given here which stands for it is heating, right? So let's calculate the oxidation number. Oxygen it is -2, potassium it is +1 as it is an alkaline metal, right? So for chlorine we don't know, we are taking it as X. So how many atoms are there? Only one atom of chlorine. So 1 plus X -6 will be equal to 0. By -6, 3 into -2. So X will be equal to +5, right? So X is equal to +5. That is for chlorine it is 5. Now moving on to KCl. Halogen it is -1, we know that. For potassium also it is +1, we already know that. And oxygen is elementary state, so it is 0. So that is what is shown here. So So as you can see here, chlorine from +5 it has reduced to -1. So chlorine undergoes reduction, and for oxygen from -2 it has increased to 0. So here what is happening? Oxidation has taken place. Moving on to the next example, 2H2O. Water is getting decomposed to hydrogen and oxygen. So here H2O, oxygen it is -2. For each atom of hydrogen it is +1. Right? And H2 and O2. Both of them are in its elementary state, so it is 0. So what happens? From +1, hydrogen has decreased to 0. So here reduction has taken place. And oxygen from -2, it has increased to 0. So here what happens? Oxidation has taken place. Moving on to the last example, sodium hydride. 2 moles of sodium hydride is decomposed to 2Na and H2. Okay. So here it is a sodium hydride. Hydrogen is in its hydride form. So hydrogen will be -1, not +1, right? And sodium is of course +1. Right, and here it is in the elementary state, so 0. Here also it is 0. So sodium +1 to 0, it has reduced, so it is undergoing reduction. And hydrogen from -1, it has increased to 0, so it is oxidation. Okay, so moving on to the next one, that is displacement reactions. These are redox reactions in which an atom or ion present in the chemical compound gets replaced by atom or ion of another element. So one element is replaced by another element, and based on whether it is a metal or non-metal being displaced, we have two types, that is metal displacement reaction and non-metal displacement reaction. So generally we can represent X plus YZ giving XY plus Z. So what is happening here? X is replacing Z here, or it displaces Z and it forms XY, and the Z is being displaced from here. So I hope it is clear. So the first one is metal displacement reaction. A metal in a compound can be displaced by another metal in the uncombined state. So a metal which is present in a compound is being displaced by another metal which is not in the combined state. So let's take an example. Copper sulfate plus zinc gives copper and zinc sulfate. So what is happening? Zinc is displacing copper from copper sulfate, and we get copper, and zinc will combine with sulfate and form zinc sulfate. Okay, here also in terms of redox reactions we are going to discuss here. So let's see the oxidation number for each of it. For oxygen it is -2, and for sulfur it is +4, and copper it is +2. Again zinc is in its elementary state, so it will be 0. Copper again in elementary state, so 0. And zinc sulfate again, oxygen -2, sulfur +4, and zinc will be in +2 state. So here you can see copper, it has reduced from +2 to 0. Oxidation number has reduced, right? So what is undergoing reduction here? It is copper. Copper is undergoing reduction. And what about zinc? From 0 it has increased to +2. So zinc is undergoing oxidation. Right. The next example, V4O2, vanadium oxide, combines with calcium to form vanadium and calcium oxide. Here also for oxygen it is -2. So when we calculate the oxidation number for vanadium, it will be +5. Right. And for calcium, as it is in its elementary state, it is 0. For vanadium also it will be 0. And calcium oxide, oxygen it is -2. For calcium it will be +2. So as you can see, vanadium from +5 it has reduced to 0. So vanadium undergoes what? Vanadium undergoes reduction. Right, it undergoes reduction. And calcium from 0 it has increased to +2. Oxidation number has increased, so it undergoes oxidation. So I hope it is clear. So this is metal displacement reaction. Moving on to the next one, that is non-metal displacement reactions. So all alkali metals and some alkaline earth metals which are very good reductants will displace hydrogen from cold water. So let's take an example, sodium. When it reacts with water, we get sodium hydroxide and hydrogen. So it will displace hydrogen, and hydrogen gas will be liberated. So sodium in elementary state it is 0. For water we have already discussed it many times. Oxygen it is -2, hydrogen it will be +1. And for sodium hydroxide, hydrogen will be in +1 state, oxygen -2, sodium +1 state. Right. And for hydrogen again it is in elementary state, so it will be 0. So sodium from 0 it has increased to +1. So sodium is undergoing oxidation. And So what about hydrogen from +1? It has reduced to 0. So it is undergoing reduction. Now another example, calcium also, it can displace hydrogen from water. So calcium reacts with water to form calcium hydroxide and hydrogen gas will be liberated. Here also calcium in its elementary state, so 0. Hydrogen in water, it is +1 and oxygen it is -2. Calcium hydroxide also CaOH twice, right? For hydrogen it is +1, oxygen it is -2, calcium it will be +2, right? Now hydrogen again it is 0. So calcium, what happens from 0? It has increased to +2. So it is oxidation. And for hydrogen it has reduced from +1 to 0. There it is reduction which is taking place. So I hope it is clear. These two examples were regarding good reductants which can replace hydrogen from cold water itself. Now we are going to talk about less reactive metals such as magnesium and iron react with steam to produce hydrogen gas. So magnesium in presence of water, again its steam means it is water itself, right? So magnesium hydroxide and hydrogen gas. Here also you can see from 0 it has increased to +2. Oxidation, magnesium undergoes oxidation, and hydrogen from +1 it has reduced to 0. Hydrogen in its elementary state, so it is 0. Here it is undergoing reduction. Hydrogen it has reduced. And next example, iron plus water, it gives Fe2O3 and hydrogen gas is liberated. Here also iron from 0 it has increased to +3. Oxidation is taking place, and hydrogen from +1 it has reduced to 0. Reduction. Fluorine is so reactive that it attacks water and displaces the oxygen of water. So fluorine is highly reactive. So what it does, it displaces oxygen itself from water. So water plus fluorine gives hydrogen fluoride and oxygen gas. Oxygen will be liberated here because fluorine is highly reactive. So in this case also, we know that in water, hydrogen is in +1 state, oxidation number is +1, oxygen it is -2. And fluorine again it is in its elementary state, so it will be 0. And in hydrogen fluoride, F, as it is a halogen, it is -1, hydrogen it is +1. And again O2 will be 0. So here also we can observe fluorine from 0 it has become -1. So it has undergone reduction. And oxygen from -2 it has increased to 0. So it has undergone oxidation. So now moving on to the last type of redox reaction, that is disproportionation reaction. So it is a specific type of redox reaction in which a species is simultaneously reduced and oxidized to form two different products. So the same element is undergoing oxidation as well as reduction by forming two different products. In one product, it will be undergoing oxidation, and in the other one, it will be undergoing reduction. So the same element is undergoing both oxidation as well as reduction. This type of reaction is possible only when an element can exist in at least 3 oxidation states. So that element must be having a minimum of 3 oxidation states. Then only it can either get oxidized as well as reduced, right? So only such elements which is having 3 or more than 3 oxidation states can undergo disproportionation reaction. So let's take an example and understand. The decomposition of hydrogen peroxide is a familiar example of the reaction where oxygen experiences disproportionation. So let's take the example of this. 2 moles of hydrogen peroxide gives 2 moles of water and O2, oxygen gas. So what is happening here? Let us understand by first calculating the oxidation number itself. So in hydrogen peroxide, it is a peroxide here. So you have to be careful. Oxygen's oxidation number will be -1, right? It is not -2. It is a peroxide. Okay. So for hydrogen, how many atoms are there? 2. So it is 2x minus 2 into 1, right? 2 atoms are there. 2 into 1 will be equal to 0. 2x is equal to 2x will be equal to +1. Hydrogen again it is +1, right? Hydrogen it is +1 and oxygen it will be -1. Now moving on to water, oxygen will be -2, hydrogen is +1, and here oxygen in its elementary state, so it is 0. So that is what is mentioned here. So you can see here and you can observe here that the oxidation number of hydrogen has not changed, but the oxidation number of oxygen, what is happening here? In one product, that is in water, what happened? From -1, it has again reduced or decreased to -2. So here reduction has taken place. And in the other product, that is oxygen, what happens in oxygen gas? -1, it has increased to 0. It has undergone oxidation. So what does that mean? The same element in the hydrogen peroxide, the oxygen is itself undergoing oxidation as well as reduction. In one product, its oxidation number has decreased, and in another product, its oxidation number has decreased. So the other element's oxidation number will remain the same. Only one element will undergo both oxidation as well as reduction. So I hope it is clear. In here it is -2 and here it is 0. Okay. Here the oxygen of hydrogen peroxide, which is present in -1 stage, here it is in -1 state, is converted into 0 oxidation state in oxygen gas and decreases to -2 oxidation state in water. So it's the same element which is undergoing oxidation and reduction. So such reactions are called as disproportionation reaction. So I hope the different types of oxidation reactions is also clear for you. So in the next session, we are going to study balancing of oxidation and reduction reactions. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.